polynomial and rational functions. Function is a polynomial if it has the following form. Here, n is a non-negative integer, and the AIs are fixed real numbers. Now, let's review a little bit of the terminology. The constants AI, or these A terms, are called coefficients. And they're the coefficients of the polynomial. If the leading term, an, does not equal 0, meaning that this is not a 0, then we say the polynomial has degree n. And the natural domain of the polynomials is all the real numbers, meaning that there's no domain restriction. Now, the range of the polynomial depends on the different polynomials. Now, we will learn how to determine this using calculus. Now, while there are lots of polynomials, there are some special polynomials. And these special polynomials are the polynomials of low degree. What makes them special is we know a lot about them, and we can do a lot with them. We will review these now. The first is the constant function. A constant function has the form f of x equals a, where a is a fixed number. Now, the constant function has some very special properties. The constant functions are polynomials of degree 0. So they are polynomials, and we say they're polynomial of degree 0. A visual representation of a constant function is a horizontal line in the xy plane. And the right end behavior and the left end behaviors are both equal to 0. And what are the right end behaviors and left end behaviors? The right end behaviors and left end behaviors are what the function goes toward as x becomes unbounded in the positive direction or negative direction. You can think of this as the function as x goes off to positive infinity, what does the function approach? And as x goes off to negative infinity, what does the function approach? The idea of what the function approaches as x goes off to infinity or minus infinity will be something we look further into when you explore functions to a greater detail. For now, we're just going to create a general expression for the right and left hand behaviors of polynomials. If an is greater than 0, then f of x goes to infinity as x goes to infinity. And if an is less than 0, then f of x goes to minus infinity as x goes to infinity. So the right end behavior is determined by using the leading term, as long as the degree is greater than 0, or degree 1, degree 2, degree n, where n is greater than 0. Now, the left end behavior depends on the power. It depends on the power of n, or the degree. If n is even, then the left end behavior is the same as the right end behavior. N is odd, and the left end behavior is the opposite as the right end behavior. So if fn is even, then and an is greater than 0, then f of x approaches infinity as x approaches infinity, and f of x approaches minus infinity as x approaches minus infinity. Similarly, f of x approaches infinity as x approaches minus infinity. So the left and the right end behaviors are the same. Well, if an is less than 0, then f of x approaches minus infinity as x approaches infinity. and f of x approaches minus infinity as x approaches minus infinity. If n is odd, then f of x approaches infinity as x approaches infinity, but f of x approaches minus infinity as x approaches minus infinity. The sign changes, or the behavior is the opposite. F of x would approach minus infinity as x approaches infinity because our leading term is negative. Because n is odd, this means that f of x approaches infinity as x approaches minus. Okay, so this is our general left and right hand behaviors for polynomials of any degree. Now, for linear functions, a linear function has the form f of x equals mx plus b. Now, here, m and b are real fixed numbers. Now, this is lines. Linear functions are lines. Not all lines, though, are linear functions. Why? Because we could have the line. Oh, let me do this again to make it a little bit more clear. We have the Cartesian plane. We could have the line x equals 2. Now, this is a line, but it's not a function. Now, linear functions are polynomials of degree 1. And a visual representation of a linear function is any line in the xy plane that is not horizontal or vertical. Because remember, the horizontal, those are our constant functions. And the vertical lines aren't functions because they don't pass the vertical line. So any line, the linear functions are perpendicular if m equals, if we have two linear functions, f1 equals m1x plus b, and f2 of x equals m2x plus b, then they are perpendicular if m1 equals minus 1 over m2, and they are parallel if m1 equals m2. And that constraint we talked about earlier, where we said it can't be horizontal or vertical. Well, linear functions won't be horizontal or vertical. Next, we have our quadratic functions. Now, quadratic functions have the form ax squared plus bx plus c, where a, b, and c are real numbers. The quadratic functions are polynomials of degree 2, and a visual representation of a constant function is a vertical parabola in the xy plane. Now, we will learn about horizontal parabolas and other conic forms shortly. We simply have a vertical parabola now. Finally, we have our cubic functions. Now, cubic functions have the form ax squared plus bx plus c, or ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers. Cubic functions are polynomials of degree 3, and a visual representation of a cubic function is given here. Now, to work with these functions, the big thing we want to know right now for any degree is determining your right and left end behaviors. And then for your linear, your cubic, and your quadratic functions, practicing finding their roots would be quite beneficial. Next, we have our rational functions. Our rational functions have, a rational function has the form f of x equals g of x over h of x, where p of x over q of x, where p and q are polynomials. Now, the rational functions, there's a few more properties we have for our rational functions. If we have p of x being one polynomial and q of x being a second polynomial, if k is the degree of our polynomial in the denominator and n is the degree of the polynomial in the numerator. If k is greater than n, the right n and left n behaviors are both equal to 0. If n equals k, then the right n behavior and left n behavior are both equal to the leading coefficient an divided by the leading coefficient bn. Whereas if k is less than n, or a degree of the polynomial on top is greater than the degree of the polynomial on the bottom, then the right and left n behaviors are similar to polynomials. And we can summarize their n behaviors using the following chart. First thing, that f of x will approach 0 as x approaches infinity, but f of x will also approach 0 as x approaches minus infinity. Now, we said when k equals n, then f of x approaches 0 as, let me try that again. F of x approaches an over bn as x approaches infinity, bk, and f of x approaches an over bk as x approaches minus infinity. Now, when n is greater than k, we have this n minus k is even and n minus k is odd. That is incredibly similar to our polynomials, because as x approaches infinity, it actually approaches these polynomials. So if our fraction is positive, then f of x approaches infinity as x approaches infinity. And if it's even, it has the same right n behavior. So f of x will also approach infinity as x approaches minus infinity. Whereas if an over bn is less than 0, then the right n behavior will be it approaches minus infinity as x approaches infinity. And the left n behavior will be the opposite. So it'll approach infinity, or it'll be the same because it's even. So fx will approach minus infinity as x approaches minus infinity. Well, what does this mean? Let's get a visual idea. So in the middle of my function, it's doing a bunch of things. It's got asymptotes, it's got some weird stuff. But my right n behavior, if I'm positive, I'll go to infinity. And if the degree, the difference between the degree is even, the right n behavior will also go up to infinity. Whereas if so this is an over bn is greater than 0, and bk is greater than 0, and n minus k is even. Well, if an over bn is less than 0, and n minus k is even, then once again, in here we've got some random stuff. We don't know what's going to happen. But because it's an over bk is less than 0, we know my right n behavior is going to go negative. And because it's even, the difference is even, the left n behavior will also be. Now, if n minus k is odd, then our left n behavior will be the opposite of the right n behavior. So if my leading terms, dividing the leading terms gives a positive number, we have f of x approaches infinity, or the right n behavior is positive infinity as x approaches infinity. But because the difference is odd, the left n behavior will be the opposite as the right n behavior. Here, if it's less than 0, then f of x, the right n behavior will be approach minus infinity as x approaches infinity. And the left n behavior will be the opposite. So it'll approach infinity as x approaches it minus infinity.